Hi guys, welcome to your last unit of pre-calc. So our last unit is on complex numbers. I'm honestly not sure what kind of background you guys have in complex numbers. I feel like you touched on them in algebra. We're just going to talk about graphing them and relating them to trig. Surprise, in our trig applications unit, we're going to trig. So we're going to start off by talking about the complex plane. So the complex plane is basically our x and y axis, except our x-axis we call the real axis, and our y-axis we call the imaginary axis. So if you have a point, or if you have a complex number, reminder, complex number, we're going to refer to them as z. Z is equal to a plus bi. The a is the real part, and the b is the imaginary part. So this will tell you how far you go on the real axis, and this will tell you how far you go on the imaginary axis. So in this case here, we have the example of our complex number is 2 plus 3i. So we go over 2 on the real axis, and we go up 3 on the imaginary axis. So this is like in just the regular Cartesian plane, just our regular rectangular good old x and y plane. This is the point 2, 3. So we will be kind of going back and forth between complex plane and not complex plane. I don't know if that's how you call it, whatever. So another term that you're going to hear me use a lot is modulus. I'm probably going to say both of them. So basically it's the absolute value or modulus of a complex number, and we write it with the absolute value bars, and it's equal to the square root of a squared plus b squared. So in the complex plane, this is the distance of our complex number from the origin. Kind of sounds like r from polar coordinates. Huh. Weird. I wonder if there's a reason for that. So, same formula. We take a squared plus b squared gives us the distance from our center up to the point. So in this case, if we want to take the modulus of z, that would be equal to square root of 2 squared plus 3 squared. So, moving on. Now we're going to be looking at this in a polar context. So this up here was rectangular. The rectangular complex plane, but then we also have the polar complex plane. So for our polar complex plane, it's the same thing. We still have our real axis and our imaginary axis. The only difference is we are measuring the distance from the origin to our point z, and then the angle from our positive x-axis up to our line here. So the angle between our point and the x-axis. So this is where we go into trig form. So if we have, I'm going to choose a different color, gray is getting boring. For imaginary number, or not imaginary number, or complex number, I'm sorry. For complex number, z is equal to a plus bi. The trig form is z equals r times cosine theta plus I sine theta, where you know r is the distance from the center. I'm going to say origin, not center. And theta So this is equal to square root of a squared plus b squared. And theta, we call this the argument, I don't know if I'm spelling that right, of z. So argument of z, and this is found by going tan inverse of b over a. Again, super familiar from polar coordinates, okay? It's almost like math builds on itself. And then we also have that a is equal to r cosine theta, and b is equal to r sine theta. So kind of like x and y. So I want you guys to take a minute, pause the video, and copy this down into your notes. This will be so helpful for you because we have 4 forms of complex numbers, okay, or 2 forms of complex and then 2 forms of, I don't know, ordinary, not complex, simple numbers. So rectangular, this is just when you have your x and y coordinate. A is your x coordinate, b is your y coordinate. We say standard form when we are in the complex plane, but we still have rectangular coordinates. So this is the case like this, okay? This is standard form right here. So for these ones, you just rewrite. You have your a and b, they don't change, okay? We've already done a lot of converting between rectangular and polar, so hopefully you guys are okay with that. With polar and trigonometric, your r and your theta stay the same, so you just rewrite these as you can, okay? So r and theta stay the same. When you are going from complex rectangular or standard form to trig, your a is equal to r cosine theta, your b is equal to r sine theta, and then to get from trig to standard, you just evaluate this. So don't worry, I know this looks like a lot. We're going to go through an example. I promise it's not that bad. And that's not just me as a math teacher saying this, okay? So for this example here, this is in what form? Standard form. That sounded like a really cheesy like game show host or something. I'm sorry I did that. Standard form. So first one, the one that's super easy to get to, is rectangular. So to get from standard to rectangular, remember all we have to do is rewrite. This is A, this is B. So we just have 1 comma square root of 3. See, I told you it wasn't that bad. All right. Now, next one that's easy, if we look up here, we can't really get from rectangular to trigonometric, so we're going to go from rectangular to polar. And again, you guys have already had a lot of practice with this. So to get to polar, we take r is equal to the square root of a squared plus b squared. So r is equal to the square root of 1 squared plus root 3 squared. Root 3 squared is just 3. So r is equal to 1 plus 3. R is equal to 2. Okay? And then theta is equal to tan inverse of root 3 over 1. So we need to ask ourselves, okay, what theta value on the unit circle, or not even on the unit circle, but this one does happen to be on the unit circle, gives us a tangent value of the square root of 3, and that would be pi over 3. Or it could be 5 pi over 3, because that's in quadrant 3 and tangent's positive in quadrant 3. However, this is in quadrant 1 because our x and our y are positive. So our polar form for this complex number is going to be 2 comma square root of 3. Now, to get from polar to complex, we just have to rewrite this. Or not, I'm sorry, not complex, trig. So trig, rewriting, we just take our R2 times cosine pi over 3, because that's our theta value, plus I sine pi over 3. And that's it. That's our trig equation, trig form. There we go, trig form. That's what I was looking for. Okay. So if you wanted to check your work, which I highly recommend always doing, you can evaluate this. So to go from trig to standard form, you just evaluate. So you distribute that 2 in. So now you have 2 times cosine of pi over 3 plus 2I sine of pi over 3. Now, you know what the cosine and sine of pi over 3 are. This is 2 cosine of pi over 3 is 1/2 plus 2I times sine of pi over 3 is root 2, or root 3 over 2. These cancel, these cancel. You're left with 1 plus I root 3. And that is what we were looking for. That's what we started with. So there is an example of doing some converting between all 4 of those forms. So these ones down here, I'm actually going to do in a separate video because I am running out of time. So if you feel like you need extra help and you want to watch that second video, go for it. Another fun little tidbit is that I don't know if you guys remember, but my favorite mathematical formula is e to the I theta is equal to cosine theta plus I sine theta. So this is where this comes from, just so you guys know. And then we can say that e to the I pi is equal to cosine pi plus I sine of pi. Sine of pi is 0. E to the I pi is equal to cosine of pi is -1. So just thought I'd throw that in there since we're working with trig form, and you guys know that I love my mathematical formulas. So if you watched that, good for you. If you shut off the video, I totally understand. So if you need more help with these, I will be making another video. Tune into that.